All right, this is section 9.3, the integral test and P-series. First of all, we're going to talk about the integral test, which if you read it there in Theorem 9.10, if f is positive, and by the way, these conditions are critical. You've got to test that these conditions are met before you can enter the integral test. So you have to have a function that's only positive values, continuous, so it has to be a continuous function, no discontinuities, at least for the part of the domain we're considering. You'll see why I just said that in a second. And decreasing. Okay. Those are the three conditions that must be met. And it needs to be all three of those things for all x's greater than or equal to 1. Okay, so keep in mind these are the three conditions that you would have to have. You have to establish that you have those three things before you can enter the test. Then, if this f is agreeing with a series, term for term, in other words, this function, if you were to use a positive integer in the function, for every time you have one of those, it would agree with a sub n. So in other words, this function contains all of the points in the series exactly. There are other points, of course, but at least for the points that are positive integer n, they agree everywhere. All right, so if you have those conditions met, then the series of a sub n and the improper integral from 1 to infinity of f of x dx. I'll finish that sentence in a second, but notice that since n starts at 1, that means that x would start at 1, and so that definite integral, that improper integral, it starts at 1, so we only have to worry about the part of the domain 1 or bigger. When x is 0 or negative, we don't care. It doesn't matter. It may have discontinuities and increase and all kinds of weird stuff going on, but as long as for x is greater than or equal to 0, the function is positive, continuous, and decreasing, then whatever the improper integral does, the series does the same thing. And the way they say that is these two things will either both converge or both diverge. So they do the same thing as the other. So since we already know how to do improper integrals, and our task in this chapter is to find the convergence or divergence of a series, we're trying to find out if the series sigma a sub n converges or diverges. And if we have a function that's positive, continuous, and decreasing for x greater than or equal to 1, we can calculate the improper integral from 1 to infinity of f of x dx, which we talked about earlier, and I'll review that, of course. And if that converges, then the series converges. If it diverges, the series diverges. Whatever the improper integral does, the series does the exact same thing. Now, the other issue that's implied here, that if you're going to do an improper integral, you have to be able to integrate f of x. If that function is one that you don't know how to integrate, or that's actually a lot of extra trouble, you might just want to go with a different test. This is not the first test you try. As I said in an earlier video, the first thing you're going to try is the limit of a sub n as n goes to infinity equal to 0 or not. If it's not, we know it diverges and we can stop right there. If it's geometric, that's the way we're going to want to do it. So this is not your first thing that you would try. There are other things you would try first before this one. And f of x needs to be integrable. If you can't find the integral for this, it's not worth trying to bat your head against the wall. All right, so let's do an example. Sigma n equals 1 to infinity n over n squared plus 1. Okay. So, we're kind of assuming we're doing the integral test if we can. So we're going to go straight to that. We're not going to worry about other tests that might work because we're trying to practice this one. So I'm not really looking for alternatives at this stage of the game. We're trying to make sure we know this technique, this test. So we're going to let f of x equal x over x squared plus 1. It's our first statement we have to make if we're going to use the integral test. Then we need to think about if x is 1 or bigger, what does that imply? Well, if you have a positive number, because of course 1 or bigger is all positive, if you have a positive number in the numerator and divide it by the square of that positive number plus 1, the answer is definitely positive. And I'm going to let you get by with just saying, it's positive. I'm not going to have you prove that one to me. You can just think about it and tell me if it's true or not. And it is. Is it continuous? Well, to find discontinuities in this is really critical. And the only discontinuities that occur for rational functions is if the denominator is ever equal to 0. And of course, that never happens for real numbers because there's no real number that you could square and get -1. So there are no discontinuities. And this is a pretty quick test as well. This is a pre-calculus level or college algebra level question, so you should be able to do that real fast. So it's positive, it's continuous. Decreasing, you might have a sense that that's true, but this is one I'm going to want you to prove to me. And if you'll remember, we talked about this once before recently. To determine if a function is increasing or decreasing, we use the first derivative test. So, doing the first derivative test, this is a fraction, a quotient, so I'm going to use the quotient rule. Low, d high, minus high, d low, all over the square of low. So that'll be x squared plus 1 when I distribute the 1, minus 2x squared, so that ends up being 1 minus x squared over x squared plus 1 squared. And I want to set that derivative equal to 0. Also consider if the first derivative ever fails to exist, because those are the two events that would make critical numbers, when the first derivative equals 0 or when it fails to exist. So the only way a fraction can equal 0 is if the numerator is 0. And if we solve that equation for x, we'll get plus or minus 1. Now realize that -1 isn't germane to this problem, but I'm going to do the whole number line analysis in a second anyway for all real numbers. And then all we have to do is conclude that for things 1 or bigger that it's decreasing if it isn't going to do that. And we already looked at this denominator. Well, actually, the square of an earlier denominator is what we have. And that's never going to happen, as we established earlier. So we aren't going to get any critical numbers from f prime of x doesn't exist because that never occurs. So I'll do the number line analysis, putting our critical numbers on there. The ones I get from equals 0, I'll put a solid dot on the number line. If I had gotten any from doesn't exist, I would have made those open circles. Okay, We will label this as the first derivative number line analysis, and we'll be discovering what that means about the function. So those are the labels you need over to the right. So if I put in a number to the left of -1, like -5, the denominator, no matter what, is going to be positive. -5 squared is 25. 1 minus 25 is negative, divided by always positive. Again, I was thinking about letting x equal -5. Negative divided by positive is negative. Then I could let x equal something between -1 and 1, like 0. 1 minus 0 is 1, so positive over always positive is positive. And then pick a number to the right of 1, like 2. 1 minus 4 is negative, divided by always positive, that's negative. So that implies that the function is going to decrease when the first derivative is negative and increase when the first derivative is positive. So that means that, let me go back up above, actually, because that's, we now know by this that starting at 1, it's a decreasing function, which is what we wanted to demonstrate. So this first derivative number line analysis establishes that indeed it is decreasing on the interval. Wow, that really looks awful. Sorry. Probably doesn't bother you as much as it bothers me. My handwriting's not so good with this pen. All right, it's decreasing on the interval from 1 to infinity, so we're good. At this point, you may say, thus, the integral test applies because we've met the conditions to enter it. Because you are going to have to tell me the name of the test you're using at some point, and since you were intentionally testing for those 3 conditions to be met, this is a good time to say that's the test you're entering. And we passed all 3, so yes, we can do that. All right, so now that we've stated that the integral test applies, we don't have to say it again later. You only need to say it once in the problem. If you end up saying it twice, no big deal. All right, so since we're doing the integral test now, we're going to write the improper integral from 1 to infinity of our function f of x dx. Well, if you recall, to deal with an improper integral, we have to change it into a definite integral by calling the end point b and changing this to go from 1 to a number b. And then we're going to force b to approach infinity. So that's one of those necessary pieces where you have to write the improper integral as a limit in order to evaluate it. Okay, so I'm thinking u substitution. If u is x squared plus 1, then du is 2x times dx. And I'm looking up there, I have the x and I have the dx. I have the x and I have the dx. All I need is the 2. So I'm going to introduce the 2 by multiplying inside by 2 and out in front of the integral sign by its reciprocal 1/2. And now I have everything to have du. Now, with improper integrals, you really don't want to do a change of variables. So I'm kind of hoping you can see the pattern here and not change to u stuff. This is one of those times where you want not want to change the variables because it's awkward. So if you need to, you can do a lemma, which is a step in the process that I don't want to show in the flow of the work. So my lemma is, what's the antiderivative of this? And since I have my du is 2x dx, this will become 1 over u du. And that's the natural log of the absolute value of u plus c. Well, it is technically that, so I'll go ahead and write it, but over here we won't need the c, okay, since it's a definite integral. So coming back, that's going to be the natural log of the absolute value of our u, which is x squared plus 1, evaluated from 1 to b. So using the fundamental theorem of calculus, we find that antiderivative, and then we substitute into it the upper limit, which in this problem is b, minus, now we substitute in the lower limit, 1. And of course, 1 squared plus 1 is 2. The absolute value of 2 is 2. All right, so as b goes to infinity, the natural log of an infinitely large thing is headed toward infinity. Remember, the natural log function looks like this. It goes up forever as x gets bigger and bigger. So the first part of this goes to infinity minus a constant is just infinity. And so what is the result of getting infinity for this improper integral? Well, what that means is that the improper integral diverges. And it's important that you tell me that, and not jump at this step, because that infinity strictly says, literally says, that the improper integral diverges. And then the next step is using theorem 9.10, the integral test, using the integral test, which we already said we were entering earlier. By the integral test, whatever this improper integral does, so does the series. So our secondary conclusion, not meaning not as important, but second conclusion we can draw, is that that divergence of the improper integral means that this series, therefore, also diverges. And in this particular one, because they always agree, you'll see the word also in these, because they agree with what one does, the other one does as well. So you'll see the word also, because that kind of implies, yeah, it's following suit. It's doing what the other one did. All right. Let's see. What's next? So let's try this one. Our series this time is from n equals 1 to infinity, 1 over the quantity 2n plus 1 cubed. Oops, didn't look very good. There we go. So we'll start with the function that's related to that series, i.e. f of x equals 1 over the quantity 2x plus 1 cubed is, so is it always positive for x's that are 1 or bigger? Well, 2 times a positive is positive, plus 1 is positive. A positive number cubed is positive, and positive 1 divided by a positive number is positive. So yes, that function is always giving us positive values for x greater than or equal to 1. Is it continuous? Well, let's look at the discontinuities. The discontinuities occur when you're trying to divide by 0, which means when is the denominator equal to 0? And that happens at negative 1/2, when x is negative 1/2. Is that a problem? Well, actually, since we're only worried about x's that are 1 or bigger, x being negative 1/2 as a point of a discontinuity does not impact us on this problem, because n is never negative in these types of series. So notice it starts at 1. So it is continuous on the interval. So we can say we have continuity on our interval, even though there's a discontinuity at a point other than in our domain, x greater than or equal to 0. And then, is it decreasing? We can do the first derivative test. If we were doing, if we do this on a paper test, if I tell you to use the integral test, then I'm going to let you just say that all of these conditions apply. So I'm going to ask that you always write them down, but if I tell you to use this test, you can assume they're all true on the interval 1 to infinity. If it's your decision, if I just say, hey, does this series converge or diverge, and you decide to use the integral test, then you'll have to make all three statements, and you'll have to prove to me that it's continuous, like I did over here to the left with this x equal to negative 1/2 is the only discontinuity, and we'd have to do the first derivative test to prove that it's decreasing from 1 to infinity. So those are the two things that can happen. Just saying that in case it's a paper test, and I tell you to use the integral test, then you can assume that all three things are true. So I'm going to pretend like this is a test question, and I've told you, you must try to do this one using the integral test. So that means we would say the integral test applies. That's what we tested, those three conditions. That's what that told us we could do. You can say applies. Another way to say that, that's also pretty good, is you can say may be used. There's a couple of different phrases that you might see in proofs of this. All right, so we can use the integral test. The first thing we do after we've established that we may use it is we go ahead and write the improper integral from 1 to infinity of f of x dx. Have you noticed that all of these are integrable? At this point, I'm not going to give you one that you can't integrate. That just wouldn't be very nice of me. So yeah, you can expect that this is going to be usually fairly easy. So to do an improper integral, the very first thing we do is we change it to a limit as b approaches infinity of the definite integral from 1 to b. And I'm going to go ahead and rewrite that 2x plus 1 that was in the denominator with a negative exponent, so that I can start to think about the integration of it. So u equals 2x plus 1. So du is 2, then times dx. I, of course, have the dx. I don't have the 2. So I'll multiply inside by 2 and in front of the integral by 1/2. And, of course, you should know that the antiderivative of a power is going to use the general power rule. So we'll have the 1/2 that was created so that we had our du. And the integral of u to the negative third is u to the add 1 to the power, u to the negative 2, so new power, divide by the new power, and we'll do this from 1 to b. So notice we're not actually changing to, oh, bother, I wrote u and I just was about to say, hey, well, notice we didn't change to u, and I did, and that's not right. That's what you want to think off to the side. So if you need to write that down off to the side, that you had u to the negative third du, which is u to the negative 2 over negative 2 plus c. You can certainly do that off to the side, but unlike what I actually did here, that 1/2 will be multiplied by not u to the negative 2, but instead what u is equal to, 2x plus 1. Yikes. Plus 1 to the negative 2 divided by negative 2. So notice we didn't actually go to u, we stayed in x. And we'll evaluate that from 1 to b. So this is the limit as b approaches infinity of negative 1/4 times 1 over 2b plus 1 squared. It's a substitution of b in, minus negative 1/4 times 1 over 2 times 1 plus 1 squared. All right. So, as b goes to infinity, since it's in the denominator increases without bound, and negative 1/4 times something that's approaching 0 will go to 0, minus 1/4, so plus 1/4 times, let's see, 2 plus 1 is 3, 3 squared is 9, so that's 1/9. And so this ends up being 1/36. Now, what does it mean for the improper integral to equal a real number? Well, because that's a real number and not infinity or negative infinity, we can conclude, therefore, that the improper integral does what? Well, since it's equal to a real number, that means that it converges. Okay. And once we've established that the improper integral converges, then by the integral test, we can further conclude that the series that's related to that improper integral will also converge. Because whatever the improper integral does, so does the series. Okay, so now I think I said in an earlier video, the integral test does not tell you to what it converges. There's actually a statement that I'm not going to do right now, and I'm not going to hold you responsible for it. But the value of the improper integral is an idea, a bound on what the sum might be, but it's not what the sum is. So in the integral test, if you look at the theorem for it, theorem 9.10, notice if it converges, the sum is found using this formula, S equals. That does not appear there, and it won't appear in most of these. I think I said last time, the geometric series and the telescoping series are generally the only ones for which we will be able to find sums. So watch for that. You can't find the sum here. So we're not going to worry about what the sum is. If we find it, it converges by the integral test. Okay. So We did use the integral test. I could have stated it here in the very last statement, also converges by the integral test. But because I said that at the outset when I tested the conditions, I don't have to say it again. So I'm not going to. All right, now we're going to move to something called a p-series. A p-series is a really simple test. It's as simple as the geometric series. Very easy to do. You have to have something that matches the form of it. So you got to be careful that it is actually of this form. You're going to have 1 over n to the p. So the exponent on n is p, and that's why it's called a p-series, because we identify that exponent with the letter p. Okay, so it's a p-series. And what that means, of course, is that when you put 1 in for n, you get 1 over 1 to the p, plus when you put 2 in for n, you get 1 over 2 to the p, plus 1 over 3 to the p, etc. So if you have a p-series, it has to look like this. It has to be 1 over n to the constant. So one thing you need to know about p is that it is always going to be a positive number. Okay, so for it to be a p-series, the only things that qualify is 1 over n to the positive number. Any positive number is fine, but you can't have like 1 over n to the -7th, for example, because that's actually n to the 7th, and that'll diverge automatically. So we really don't talk about p-series if p isn't positive. It has to be positive to enter the p-series test. So that's what the p-series looks like. So let's talk about the first possibility I want to encounter is, what if p is 1? Well, that p-series, if I raise in the denominator n to the first, I get just n, and that's 1 over 1 plus 1 over 2 plus 1 over 3, etc. Remember, I gave this as a named series in the last set of videos. This is a special series called the Harmonic Series. So the Harmonic series is actually also classifiable as a p-series. And this is how I want to address whether it converges or diverges. But to establish that, I'm going to have to employ another test. Then after that, once we've established whether this series converges or diverges, once we've proven it, then it's always going to do that, and you won't have to reprove that for me. So we're going to prove it once and go with that. So this is a harmonic series. So I'm going to let f of x be 1 over x. F is positive as long as x is greater than or equal to 1. The discontinuity occurs when the denominator is 0. Of course, x equals 0 is not in our domain. We're only worried about x greater than or equal to 1, greater than or equal to 1, so it's continuous. And 1/2, 1/4, 1/3, 1/2, 1/3, 1/4, those are getting smaller and smaller. And again, I'm going to let you get by with just saying so. So it meets all the conditions to use the integral test, which is what we're going to do. So since I'm saying the name of it here, I won't have to say it at the end again, unless I forget and just happen to say it again and write it again. No big deal. if you do. So we form the improper integral from 1 to infinity of 1 over x dx. The antiderivative of 1 over x dx is the natural logarithm, the absolute value of x. Oh, rats. Well, I'm doing what some of you do. Don't do that. I did not do the first step, which is to do what? Can you tell me? The very first thing you have to do with an improper integral is rewrite it as a limit. So please don't forget that, of a definite integral from 1 to b as b goes to infinity. Glad I caught myself before I'd written too much. Kind of embarrassing when I do that. The antiderivative of 1 over x dx, of course, is the natural logarithm of the absolute value of x, evaluated from 1 to b. That's the limit as b approaches infinity of natural logarithm of b. I can actually get rid of the absolute value because we're only worried about values of b that are bigger than 1. So that's definitely already positive, so I don't need to worry about the absolute value. Minus the natural log of 1. Of course, the natural log of 1 is 0. And as b goes to infinity, the natural log of an infinite thing goes towards positive infinity. So that means that the improper integral 1 over x dx from 1 to infinity diverges. Okay. And since it diverges, that implies that our series, the harmonic series, if we want to call it by its name, but the series is 1 over n, also diverges. So we've just proven that the harmonic series diverges, and so from now on, if you ever need to just know that one, you can just claim that the harmonic series diverges, and you don't have to prove it to me. What we just went through is that proof, but you won't have to go through that for me ever. It wasn't that hard to prove. So, but anyway, that says that we know that the harmonic series diverges. So go back for a second. If p is positive, there are 3 cases. We talked about this before, the trichotomy idea. P could be, since it's already positive, it could be between 0 and 1. It could be 1, or it could be bigger than 1. And those are actually the divisions that make sense in this problem. And what we just proved is that when p is 1, it's the harmonic series, and it diverges. Okay, the p series diverges when p is 1. So, the rest of this is that if p is between 0 and 1, it will diverge as well. And if p is greater than 1, the series will converge. Okay. So, combining these 2 ideas, the test is if p is between 0 and 1, including 1, the series diverges. So that's one of our conclusions, if it's a p series. The other conclusion is if p is greater than 1, the series converges. This is kind of a tricky thing that you've got to get in mind. And I'm going to go ahead and put it in your mind right now so that you realize that you might conflate these 2 ideas accidentally. So The two possibilities were the absolute value of r is less than 1, or the absolute value of r is greater than or equal to 1. This was convergence. This was divergence. So be very careful here. When r, let's just, I'm not going to say absolute value because you know you're supposed to do that. If r is bigger than 1, it diverges. But if p is greater than 1, it converges. Just the opposite of what you might have expected. So don't conflate these two. And if r is less than 1, I know it's absolute value, but if r is less than 1, it converges. Whereas if p is less than 1, and still greater than 0, but if p is less than 1, it diverges. So make sure that you go the right way. We're comparing to 1, so that's similar, but you get different conclusions for greater than 1 and less than 1 in each case. So be very careful that you pay attention to these two tests. Notice that the or equal to 1 is always divergent. So if p equals 1 or r equals 1 or negative 1, it's divergent. So make sure you put the or equal to in the right spot as well. All right. So that's the tricky thing you're going to have to watch out for, that you don't accidentally conflate those two. All right. So let's do maybe one example, and then I'll go to another video. So the directions say to determine the convergence or divergence of each of the following series. So 1 plus 1 over the cube root of 4 plus 1 over the cube root of 9 plus 1 over the cube root of 16 plus 1 over the cube root of 25. The challenge here in this particular case is when they give you the expanded series, you're going to want to have the general term so you can find out what kind of series it is, generally speaking. That's what you want to do. You might notice this is not geometric because there's nothing I could multiply by 1 over the cube root of 4 to get 1 over the cube root of 9 that would also multiply by 1 over cube root of 9 to get me to 1 over cube root of 16. So it's not geometric. The numerator is always 1. You might notice that we're always taking the cube root of something. We're always taking the cube root of a perfect square. So I'm going to call this n squared. And for the first one to give me 1 over 1, the denominator is 1, that would mean that n would have to be 1 to start with. And when it's 2, I'll get the 4 in the second denominator. When it's 3, I'll get 9 in the third denominator. Okay, so I've written that in that form of the sigma notation. Then, and you may have to rewrite and do some algebra here, what is that radical the same thing as? Remember how much we don't like radicals in calculus anyway. We usually go to a power anyway. What power of n is that? Well, it's 2/3. And that is a p-series. So if you tell me it's a p-series, you've told me that's the test you're entering. So it is a p-series. Then I'm going to ask you to identify the value of p. P is the exponent on n, so p is 2/3. And then I'll say since, remember there's no absolute value with the p-series, since p is between 0 and 1. Notice I'm not writing that 2/3 is between those. I'm writing this test statistic, the thing that's circled there in pink. I'm looking for that expression to tell me whether it converges or diverges. The series from n equals 1 to infinity of 1 over the cube root of n squared diverges. And notice how quick and sweet this test is for the convergence or divergence of a series. P-series is actually really fast, so it's a good one. All right, I'm going to close this and go to a new video.